With this we conclude mobile IP and what are the various scenarios that are possible with mobile IP regarding transfer of the packets from one network to another network, or location of the agents, or encapsulation of the packets, or even registration of the mobile node. So, we have seen all possibilities in case of mobile IP networks. Now, we look at another topic, which is mobile TCP, and we understand we should first understand that mobile TCP would be quite different from the normal TCP that we are using. The normal TCP mechanisms used with fixed networks don't work very well for mobile networks. The very reason being that we can expect a lot of transmission errors in case of a mobile scenario, unlike in a fixed network. In a fixed network, the number of errors are relatively limited. Okay, whenever you have a sender and a receiver, both are fixed, then there are relatively few errors. Okay, you send them through a transmission medium like a fiber optic cable or something else, so transmission errors are limited. But in the case of a mobile scenario, let us say you are sending from a fixed node to a mobile node, then different types of transmission losses might be possible. Okay. And the losses might also have to do with the environment conditions. Okay. And the losses may also have to do with collisions, packet collisions. Okay. You have the hidden terminal problem and far and near terminal problems, where collisions occur with other nodes and your packets are destroyed. So, the chances of losses are more in the case of wireless networks when compared to the fixed wired networks. Okay. So, this is the context in which a mobile TCP has to be defined separately, let us say between a fixed node and a mobile node, or between two mobile nodes. Okay. But between two fixed nodes, you can always use the normal TCP, okay, normal transmission control protocol. And again, if we look at the different types of transmission control protocol mechanisms, okay, in mobile networks, we predominantly have three types, which is ITCP or indirect TCP, MTCP or mobile TCP, and snooping TCP, something called snooping TCP. In fact, in all these types of TCPs, we assume there is a connection between a mobile node and a fixed node, and that fixed node and another fixed node. Okay, right? So there is a connection between a mobile node to a fixed node, and that fixed node to some other fixed node. Looking at indirect TCP, okay. Indirect TCP suggests splitting the TCP actually into two layers, okay, into actually two TCP sublayers. One between the mobile node and the base transceiver, okay, and the base station BTS. And the other one between the BTS and a fixed node. In fact, you can see BTS mobile or fixed? Is BTS fixed or mobile? We assume BTS is fixed, okay, and will be serving the mobile node as well as the fixed node. So in fact, looking at another point of view, another diagram, it gives another viewpoint. Here you have an access point. Access point is nothing but the BTS we are talking about earlier. Okay? Access point is the BTS, that is the mobile node, and this is the fixed node. Fixed node. Then indirect TCP recommends using the standard TCP, normal TCP, okay, between the fixed node and the access point, and between the access point and the mobile host, it suggests using something called a wireless TCP, a modified, optimized TCP, an optimization of TCP. So what is the advantage? Okay, in fact, the advantage is that you don't need to modify entirely the existing TCP. The TCP in the fixed network can be used as it is without modification, while only the TCP in the mobile part needs to be slightly modified. You don't need to completely define a new protocol. That is one advantage of using indirect TCP. So no changes to TCP protocols for the hosts which are connected to wired networks or fixed networks. So they use normal TCP. While we use optimized TCP for mobile hosts. So obviously there is no end-to-end connection. Okay, really seeing there is no end-to-end from the fixed node to the mobile node. Actually there is one connection from the fixed node to the access point and another connection from the access point to the mobile node. But there is no direct connection between the fixed point and the mobile node. Also another advantage is that the nodes which are in the fixed part of the network, which are between the fixed, which are connected to the access point and they are fixed, okay, the fixed nodes. They are not affected by the mobile nodes, by the characteristics of the mobile nodes. So any losses in the wireless part, okay, in the mobile node part of the network will not propagate into the fixed part of the network. Fixed part of the network will still carry on its job like normal TCP, while the mobile nodes may have special mechanisms to deal with errors. Okay. So these mobile nodes errors may not creep into the fixed nodes, fixed part of the network. That is another advantage of using indirect TCP. And in fact this is the most widely used protocol. It is used by millions of hosts. Okay. Though there are several versions, it is economically feasible and it has some good advantages. So it is used. Now we come to the diagram we were talking earlier. Earlier we were talking about a base transceiver. Okay. Mobile node connected to a base transceiver and the base transceiver connected to a fixed node. And that fixed node is connected in fact to the TCP-F. Fixed node is connected to another fixed node TCP-F dash. Okay. So actually we see that the base transceiver is taking care of serving the mobile node and the fixed node. It is like an agent. It is the access point between the mobile node and the fixed node. The access point here is the base transceiver. And you can see these are single hops. From the base transceiver to the fixed node, transmission is done in single hop. Okay. While from fixed node, even from mobile node to base transceiver, transmission is done in simple single hops. While between fixed host and the fixed host, the transmission can be in multiple hops. There can be multi-hop transmission between TCP-F and TCP-F dash. And you can see one very important thing you have to observe here is, one is the layer diagram in the home network and the other one is the layer diagram in the foreign network. So whenever something like a handover takes place, the base transceiver in the home network must hand over to the base transceiver that is present here in the foreign network. So TCP-M has to hand over to TCP-M dash, okay, whenever a handover occurs. So you can see the mobile node TCP-M sends and receives data to the fixed node TCP-F in the diagram, and we can see there is a single hop between the mobile node and the BTS, which is indicated by TCP-M, okay, and also between BTS and the fixed node, which is indicated by TCP-F. It is single hop transmission, but between TCP-F and TCP-F dash it is multi-hop. It is multi-hop transmission. So we don't bother even there is delay between TCP-F and TCP-F dash, okay, because in a wired network, we expect delay, but in a wireless network we expect faster transmission. We expect much faster transmission. And you can see the data streams that are received from MN are buffered at TCP-M, which is the BTS. So BTS is acting as an agent, okay, it is acting like an access point in the previous diagram between the mobile node and the fixed node, and it is buffering any data that's coming from the mobile node. And again the TCP-F would send that data. Once it reaches, it sends the data to another fixed node TCP-F dash. Okay. And we have seen that in case of handover, TCP-M has to hand over the entire state, current state, including the current socket number, port numbers it's using, along with the current data, current state of data to the new TCP-M dash, okay, to the new base transceiver. So handover involves in substantial delay in case of indirect TCP, which is another disadvantage of indirect TCP. Obviously this is indicated by the same. In case of handover, packets for transmission must be transferred from TCP-M to TCP-M dash, and also the present state of the socket has to migrate from TCP-M to TCP-M dash. Latency. Again, to recapitulate the relative advantages and disadvantages of indirect TCP in order, if we look at the order of importance, okay, the best advantage that indirect TCP provides is it isolates the fixed part of the network from the wireless part of the network. So any errors in the wireless part of the network will not affect the fixed part of the network. They will not propagate to the fixed part of the network. That is the basic advantage. Another advantage is you don't need to completely modify the existing TCP protocol. You can use the protocol as it is between TCP-M and TCP-F, and between mobile node and the TCP-M you can slightly modify, okay, the TCP-M mobile, okay. TCP-F stands for the fixed TCP protocol and TCP-M stands for the mobile TCP protocol. So that mobile TCP protocol needs to be slightly modified, whereas TCP-F is same as the normal TCP protocol for wide networks. Okay. So even though you are using it between a BTS and the fixed node, BTS is assumed to be a wireless station. It is a wireless station that is fixed. Whereas the mobile node is wireless and it is moving. Okay. So even between BTS and fixed station, you can use the normal TCP, which is TCPF. Whereas the other TCP, TCPM has to be slightly modified. Okay. So this results to an ease of implementation. Okay. That is another advantage of indirect TCP. Yet another advantage you can see is the retransmission time between the mobile node and the fixed node. So whenever a disconnection occurs, the retransmission time is quite good. Okay. The time for retransmission will be quite good because data is buffered at the transceiver station. Okay. So that is another advantage of your indirect TCP. However, when it comes to disadvantages, we have seen that there is no end-to-end connection. Both the ends will terminate at the access point only. Okay, both the fixed end and the mobile end will terminate at the access point or the foreign edge. So there is no end-to-end reliability. Okay, for example, there is no guarantee that some data that is sent by the mobile node will finally reach the fixed node. It may reach the access point, okay, but there is no information for the fixed node that it has reached, it will reach it. Okay, so the fixed node will not absolutely know whether the information finally reaches it or not. Okay. So end-to-end reliability is not guaranteed. That is one disadvantage. Another disadvantage is the handover latency. Whenever a handover occurs, we have seen that the entire state of the socket for TCPM along with the data has to be transferred to a new BTS base transceiver station in the foreign network. So this transfer of entire state will result in delay, will result in a substantial delay. So handover suffers from delay in case of indirect TCP. So that is the reason for possible loss of information at the base station. And you can see, since end-to-end reliability is one requirement for TCP, and this indirect TCP violates that very requirement. It doesn't guarantee end-to-end. It doesn't guarantee reliability from a fixed node to a mobile node, but it will guarantee reliability from fixed node to the access point and mobile node to the access point, but it will not guarantee reliability directly from fixed node to the mobile node. So the very purpose of TCP is lost. Okay, but still you can see indirect TCP is very widely used across millions of hosts because of its simplicity. I told you, because it doesn't require too much modification is one thing, so cost effective to implement, and also buffering requires space which is cheaper nowadays. Okay, people don't bother buying hardware for buffering as the storage costs become cheaper. Okay, so obviously the simplicity of implementation makes indirect TCP most widely used in spite of its disadvantages. And you can see, in fact, these statements indicate the serious problem of buffer overflow in case of indirect TCP. You can see there is something called a transmission timer. Okay, you can see there is something called a transmission timer. So whenever a disconnection occurs, until that retransmission timer resets, okay, it would remain disconnected. Okay. But in the case of mobile TCP, what it implies is, let us say there is a disconnection has occurred, okay, and the BTS is buffering the data from the mobile station, but it has immediately reconnected. It reconnects, the mobile station has immediately reconnected. But still, since the retransmission timer will be set to some fixed period, even though the mobile station has reconnected, it keeps on buffering data. That what do you call BTS keeps on buffering data even though the connection has been established very quickly, re-established very quickly. So that leads to that may lead to a overflow in the buffer, overflow of the buffer. Okay. In fact, this is for this reason that mobile TCP is introduced. Something called MTCP is introduced. Okay. And we need to understand that whenever there is a disconnection, in case of indirect TCP, it continues from that time. Okay, from that time, the data till that time has to be maintained, has to be buffered and maintained. But mobile TCP provides another solution where we don't require any buffering at all. Okay, the BTS will not buffer data, but it will try to hand over to another BTS. Okay. So you can see there is no, when you look at mobile TCP, there is no concept of buffering at all, which avoids the problem of this congestion, buffer overflow and all these things. Okay. But it has to hand over extremely fast to another station, BTS, okay, in case of handover. Okay. However, in case of disconnection, it would require more time. Okay. We'll see what's the reason. Right. And in fact, you can see whenever a handover occurs, your mobile TCP says reset the window size to 0 when the handover occurs, whereas your indirect TCP says continue with that window size, continue with the same window size. Here it involves in resetting the window size to 0, and then after the handover has taken place, then again it resets to the older value of the window size. Okay, then it resets to the older value of the window size, whereas there is no resetting of window to 0 in case of indirect TCP. It continues from where the error has occurred. And you can see this is the diagram for mobile TCP, where instead of TCP-M there, here you have something called a supervisory host SHM. SHM stands for supervisory host. Okay. So you can see supervisory host is between the mobile node and your fixed node TCP-F. Again, the TCP-F is connected to another fixed node TCP-F dash. So if you look at mobile TCP also, like indirect TCP, suggests splitting the connection into two parts. One part between the BTS and the fixed node, and the other part between the BTS and the mobile node. However, whenever a handover occurs, it suggests to set the window size to 0. Okay. In fact, we need to talk about what is what is slow start and transmission. What is the retransmission policy in case of normal TCP? To understand this, to understand the window size. Okay. Just to recapitulate what is window size. Okay. You know, always the receiver has to maintain a window that corresponds to the number of packets that can be sent without acknowledgement. How many maximum packets can be sent by the sender without an acknowledgement, since the last acknowledgement is maintained by a window size. Okay, a congestion window, that's called a congestion window. And again we have something called a congestion threshold. Okay, every time a parameter called congestion threshold is defined. Okay. So in normal TCP, the transmission policy is whenever there is a loss in acknowledgement, whenever there is a loss in acknowledgement or a disconnection, then initially increase the congestion window exponentially. Getting me or not? Okay. So first initially make it 2, then 4, then 8, so on, until it reaches the congestion threshold. Okay. Thereafter it increases linearly. Thereafter it should increase linearly. Okay. Yeah, generally if the transmission is successful. Okay, that is not in case of missing acknowledgements, if in the normal case. Okay. But however, whenever you find a missing acknowledgement or data, then the method is to half the congestion threshold by half, which means you are also reducing indirectly the congestion window. Okay. Reducing the congestion threshold also means reducing the congestion window indirectly. Reducing the congestion window means sending less data. Okay. Sending slowly, forcing the sender to send slowly. Okay. That is the general mechanism in case of normal TCP. Do you all remember this? Okay. So whenever there is a missing acknowledgement, then the congestion threshold keeps reducing, and in effect the congestion window will also keep reducing, because only until congestion window data can be sent fast. Agree with me? Only until congestion threshold data can be sent fast within the congestion window. If you are reducing the congestion threshold, that means you are also reducing the congestion window effectively. That means you are able to send only less data. That means you can send slower, you need not send fast, you can send data, the sender can be sending data slowly. Okay. So this is the window we are referring to, this is the congestion window we are referring to. When we are saying set the window size to 0, okay, we are setting the congestion window size to 0. Okay. Setting the congestion window to 0 will result in something called freezing. Okay. Nothing happens. The sender will not send, the receiver will not receive, no buffering will be done, nothing will be done. It temporarily freezes. Okay. So whenever handover occurs in mobile TCP, the congestion window is set to 0 until the handover takes place. After the handover takes place from one BTS to another BTS, then again it is reset to the previous window size, that congestion window size which was last there at the beginning of handover, it is reset. Okay. So the new supervisory host, SCH we are calling here, will start with that congestion window size. Okay. However, you need to understand that there is no concept of buffering in case of mobile TCP. Okay. There is only remembering the window size, okay, and transferring the window size that happens from one supervisory host to another supervisory host. Okay. But there is no concept of buffering. And you can see SHM refers to the connection between the mobile node and the BTS. Okay. And another TCP connection we are referring to between the fixed node. Okay, in fact, one connection is between the mobile node and the BTS, and the other connection is between the BTS and the fixed node. BTS and the fixed node. So BTS has an access point. BTS serves like an access point for SHM connection, and SHM can send or receive packets, okay, through BTS. From the mobile node, SHM can send or receive packets. But SHM can send and receive packets, okay, to and from the fixed node. Okay. It is acting like an agent between the mobile node and the fixed node and TCP F dash. Okay. So SHM is acting as a mediator between MN and the TCP F. So whatever data is coming from the fixed node, it is forwarding to the mobile node. Okay. And again, whatever data is coming back from the mobile node, it is forwarding to the fixed node. And you can see again here also the communication between mobile node and SHM and SHM and TCP/F is single hop, but between TCP/F and TCP/F dash it is multi hop. In fact, retransmission delay between the BTS and the fixed node doesn't take place. Okay, between the fixed node and the what do you call as BTS, there is no retransmission delay. However, there is retransmission delay between the mobile node and the BTS. Okay, in fact, you can see retransmission delay here is more, while the handover delay is less. It is the opposite to indirect TCP, where handover occurs slowly, okay, but retransmission occurs quickly in case of indirect TCP. But here it takes time to retransmit. Retransmission takes time, but handover takes less time, because immediately it is handing over to another SHM dash. That SHM will hand over to another in a foreign network. Okay. So when is disconnection detected? Disconnection is detected when SHM is not receiving any acknowledgements from that mobile host. Okay. In which case it will immediately set the window size to 0, congestion window size to 0. Okay. And then when again SHM starts receiving packets, it will reset that window to the earlier value of W. And you can see error detection and correction are done at the both ends, but not at SHM. Here SHM is only used to track the window size and when disconnection has occurred, and to transfer to another SHM dash in case of handover. Okay. But it will not perform anything else. It will not perform buffering, it will not perform error correction. Whereas in indirect TCP, everything is carried out by the BTS. There is a large load on your BTS, right? And also you can see the header could be compressed and sent to the mobile node. We were looking at something called Van Jacobson compression and other mechanisms. So header can be compressed and sent to the mobile node, okay, which would reduce the delay to some extent in order to reduce the transmission delay. And you can see whenever there is a handover, there is no buffering of the packets by the supervisory host SHM, and no packets need to be transferred. Even the socket information need not be transferred. It will set up a new socket Okay, the new SHM dash will set up another socket number and no packets are needed to be transferred. Okay, and SHM sets W to 0. Only thing it needs to transfer is the window size, the earlier window size that is used by SHM dash. Okay. So handover takes place very quickly because earlier you had to transfer packets also. In indirect TCP, you had to transfer the entire packets also to the new agent. But here you are not transferring any packets. Okay, you are immediately handing over to the new agent. Getting me? So handover time is very less here. Handover time is very less, but retransmission time might be more. Again, you will have to retransmit all the packets. Okay. There you need not have to retransmit the packets because you have already buffered and sent, but handover time is high because you have to also send those buffered packets to the new agent. So this is how your indirect TCP and mobile TCP compare with each other. Okay. That's the reason I felt unless you know indirect TCP, you can't better appreciate what is mobile TCP and why it is required. So you can see again coming back to the advantages of mobile TCP. Mobile TCP requires the entire protocol to be modified. Okay. The entire protocol between the mobile node and the fixed node must be completely modified. That protocol applies between the two ends. End-to-end reliability between the mobile node and the fixed node is guaranteed when you use mobile TCP. Okay. However, modifying the entire protocol is a costly process. It is a tough, complex process. So it is complex. Mobile TCP is complex to implement, but it guarantees reliable end-to-end delivery. And while indirect TCP is used in scenarios where there are long disconnections, the disconnection period is long, but disconnections occur very less often. They don't occur very frequently. Mobile TCP is exactly the opposite case. Mobile TCP is used in cases where there are many frequent disconnections. When you can expect many frequent disconnections, then mobile TCP is used. When you don't expect many disconnections, but you expect lengthy disconnection for long time, okay, then indirect TCP is used. So in fact, as I told you, the very reason why mobile TCP is introduced is to prevent that congestion problem, buffer overflowing problem in case of buffer overflow problem in case of indirect TCP. We have seen that even though indirect TCP works well only if the disconnection is for some sufficient time. If it reconnects very fast, still there is no advantage in indirect TCP because until the transmission timer is reset, it will keep on buffering. Even though the connection is retained, it will keep on buffering. So to eliminate that problem of indirect TCP, mobile TCP has been introduced, and it deals with frequent small connections. Okay. While indirect TCP deals with infrequent lengthy disconnection. However, what are the disadvantages? If you look at the other side of the coin, the fixed part is not isolated from the mobile part here. So any errors in the fixed part of the network will automatically affect the mobile part of the network. You are not looking at it separately like you have done in indirect TCP. Okay. So any problems due to or any delays due to the fixed part, due to the wireless part, will also affect the receiver. Okay. So any delay in the fixed part, wireless part of the network will also delay the fixed part from receiving. So that is one disadvantage. And if you are required to reset frequently that window size to 0, okay, then you are incurring a lot of bandwidth, because resetting the window size to 0 and again retaining the window size and transmitting all requires bandwidth. And the bandwidth changes, frequent bandwidth changes have to be considered whenever the resetting of the window size is done. So whenever you reset the window size to 0, low bandwidth is required. Whenever you are getting back that window size, the bandwidth will suddenly increase. So it will lead to decrease and increase in the network. Okay. It will lead to increases and decreasing of the bandwidth in the network, which we have to deal with. And mobile TCP assumes it has a very big assumption, underlying assumption, that the error rates in the network are relatively low. Okay. In fact, it was found that mobile TCP very badly in case there are too many losses in your network. Okay. If your bit error rate in your network is very high, then mobile TCP doesn't perform well. It works fine as long as the error rate in your network. Also, security risks, any compromise in the supervisory hosts might result in setting that window size to wrong values or performing some sort of attacks like that. Right? The window size, for example, could be advertised to a wrong value to another supervisory host, and it is not actually where you have to start from. So you are unnecessarily again sending unnecessary packets, which is wasting your bandwidth in your network. So such attacks are possible. Of course, always attacks are possible if TCPM is, the BTS is compromised also, or supervisory host. Any intermediate entity is compromised, then they can be attacked. If your foreign agent is compromised or your home agent is compromised, attacks are possible. Same is the case here. Right? In fact, we know that mobile TCP takes some time for retransmission. It takes more time than indirect TCP does. Okay. However, we have seen that it is quite good in handover. When it comes to handover, it does very fast, but for retransmission, it takes some time. So in fact, an improvement has been introduced in mobile TCP to reduce the retransmission time. That improvement is exactly called fast retransmission. Okay. In fact, this mechanism of fast retransmission is also so earlier we have talked about the congestion window size being reduced whenever there is a missing acknowledgement, forcing the sender to send slowly. We are forcing the sender to send at a smaller rate. However, there are cases where we will force the sender to send by sending duplicate acknowledgement. Okay. In fact, whenever there is a congestion, okay, whenever there is a loss in the network, we are assuming that it is due to congestion, but it may not necessarily be due to congestion, but it may also be due to the congestion that occurs might not necessarily be due to packet losses, but it might also be due to errors in the transmission. Okay. So how can we differentiate between a packet loss and the errors in transmission? In fact, in TCP what we do is, the receiver, let us say, receives wrong packets. Okay. Then what he does is, he sends back acknowledgement to the sender, say giving the sequence number that he is expecting. He will say, this is the sequence number I am looking for. Okay. While the sender is sending some other sequence number. Okay. When he does it 3 times, when he sends the sequence number that he requires 3 times, then the sender will be forced to transmit quickly. He will be sent to transmit fast. Okay. Why? Because he understands that there is no disconnection, but data is being transmitted, but it is the wrong data that is being transmitted. So what does he do? He takes care of correcting the data and sending it fast to make up for the lost time, because some time has already been lost in sending wrong packet. To make up for that lost time, the sender will start transmitting fast. So 3 acknowledgements by the receiver with the expected sequence number will force the sender to transmit at a faster rate. That is called fast retransmission. Okay. Mobile TCP uses the same mechanism when in the case of a handover. Whenever there is a handover from one supervisory host SHM to another supervisory host SHM dash, okay, by default the new host will start with a slow transmission. We can't call it a retransmission, but it will start with a slow transmission. But however, in mobile TCP what could be done is, as soon as the mobile host registers, okay, at a foreign agent, in a foreign network, it will send 3 duplicate packets. Okay. In fact, it sends duplicate packets to the corresponding host, forcing the corresponding host to enter into fast transmit mode rather than slow transmit mode. So whenever a handover occurs, the transmission speeds up. It will not slow down, but it will speed up. Why? Because we know that during transmission already some packets might have been lost. Some time is lost. Now we are making up for that time by transmitting fast. If we slow down, it might even add to the problem. Already there is a loss in time because of handover. Now if you again start slow, transmitting still slower, the problem might aggravate. Okay. So for this reason, whenever there is a handover, the sender will be requested to send at a faster rate, not at a slower rate. That is called a fast retransmission policy in case of mobile TCP. So it is an optimization in mobile TCP which improves the performance, of mobile TCP. And see, the advantage of this fast retransmit and recovery approach is that very minor changes, okay, to the host software might also be required. Even the corresponding node software also must be changed to make it transmit faster, but that modification is a very small one. Yeah, in fact, it is the mobile node software that has to be changed, but the corresponding node software does not even need to be changed. And this method works well only if the handover period is sufficiently small. If the handover period is large, then anyway the corresponding node will start retransmitting. You don't need to transmit fast. Okay. Even before you do that, it itself will start transmitting. So there will not be a need. But only if the handover period is sufficiently small, then you can force the corresponding node to transmit fast to make up for the lost time. Okay. Otherwise, it will do it by itself anyway. Okay. So by the time you tell it to transmit fast, it might have already transmitted many number of packets. So it will not work in that case. Right. And now we can understand that in indirect TCP actually we said there is no end-to-end reliability. There is end-to-end reliability. The reason is the access point or the foreign agent is listening only to at a time. It is either listening to the fixed node one time, acknowledgements from the fixed node at a time, or it is listening to acknowledgements from the mobile node at one time. It is not listening to acknowledgements from both ends at a time simultaneously. That is the problem why end-to-end reliability is not guaranteed. Okay. Now you can simply understand that if you can modify the foreign agent to listen to both acknowledgements at a time, it is listening to acknowledgement from the fixed node as well as the mobile node, right? Then it can decide that if both acknowledgements are successful, then probably the packet has been successfully transferred from this end to that end. That is exactly the concept behind snooping TCP. In fact, in snooping TCP, the foreign agent will snoop. Snoop is to listen, to drop your ears and listen, is snooping. So foreign agent will be listening to acknowledgements in both directions simultaneously. It will listen to this acknowledgement as well as that acknowledgement, which will guarantee that data would be sent in both directions, end to end. It reaches end to end. Okay, and you can see whenever it sees that any data in one direction is lost, it immediately retransmits data in that direction. If it sees data and on one link is lost, it will immediately send that lost data to that without any delay. And again, this requires change in only foreign agent or the access point. It doesn't require you to change the node or the fixed host. So in fact, it's like transiency, A to B and transitivity. Okay, A to B and B to C implies A to C. There is one from B to reliability is simultaneously checked from B to A and B to C. Obviously, there is also reliability from A to C. So you can see the foreign agent listens to both directions. And however, any losses in the mobile node, any losses in acknowledgements are treated as negative acknowledgements. In the wireless part, it treats as negative acknowledgements, and in the wired part, it treats as no acknowledgements. Okay, positive acknowledgement is success. Negative acknowledgement in the mobile node is failure in the wireless part, and no acknowledgement is failure in the wired part of the network. Okay. So that way it checks for the three cases, whether the acknowledgement is positive or negative or no acknowledgement. And the entire responsibility is obviously on the foreign agent. It has to reorder and transfer the packets also. Okay. Let us say there is a disconnection on one end, then it has to buffer those packets and then send the lost packets to the other end. Okay. So all this is the responsibility of your foreign agent, okay, the access point. So snooping TCP is very good if it works, but it is very, very complex to implement. Okay. Too much functionality is on the foreign agent. So it's complex to implement.